So, right. So this is the fifth lecture, but this has nothing to do with fifth. So I'm going to. I thought I would give one lecture about Hilbert's fifth problem. The reason is that the techniques that go into the proof of Hilbert's fifth problem are the techniques that we use in this work with Green and Tao on the structure of theorem for approximate groups. So, in order to understand the proof of the structure theorem, it's important to be able to understand the proof of the Montgomery, Gleason-Yamabe theorem that solves Hilbert's fifth problem. Okay, so today I will just focus on Hilbert's fifth problem and try to explain the ideas that come into the proof. So it's old mathematics in the 1950s, but surprisingly, the mathematics that come into the proof of that theorem have not been used so much in the last 50 or 60 years. So I guess this justifies a bit the need to explain it in one lecture. So let me remind you what Hilbert in 1930. What was his fifth problem? So it's this series of 23 problems, and the fifth one is about Lie groups. It's about continuous groups. So this was maybe a few decades or 20 years or 30 years after he introduced the notion of the Lie group. And Hilbert's fifth problem is about removing the differentiability from the definition of the Lie group. So when you read this page and a half where this problem is explained, there are various ways to interpret what Hilbert is really looking after. But let's say in vague terms, he wants to say that if a group acts on a manifold continuously, on the manifold, so is this action differentiable? So this is rough terms. Okay, so that's the rough problem. Before Hilbert, Lie and Shaw had already showed that if you have a look for a group, and you know that the multiplication and the inverse are C2, then in fact they are analytic. So the question is really going from C2 to just continuous multiplication now. And here, it's not completely clear in Hilbert's formulation whether he wants to look at a given group acting on itself by multiplication, or whether he looks at a group acting on a manifold. I think he looks at a group acting on the manifold when you read it. Because at that time, people were not so much interested in groups on their own, but rather they would see groups as subgroups of operators acting and so on. So there's a beautiful Bourbaki report of from the 1950s, 1951. This is basically a year before the theorem or the problem was solved. It's a beautiful Bourbaki report. Usually, nowadays we tend to write a Bourbaki report after the fact, after the theorem is proved, right? But in those days, you could write Bourbaki reports before the theorem is proved, and it makes it more exciting. And it's actually a very nice account of the problem, right before it was solved. And so you can see exactly, he says exactly what needs to be solved, and then a year later, Gleason and Yamabe did it. So, and in this Bourbaki report, he identifies two problems. So this problem A, which is sometimes called Hilbert's fifth problem, so a locally Euclidean topological group in the group. And problem B, a locally compact subgroup of homeomorphisms of the manifold is a Lie group. Okay, so these are the two problems, of course. Yeah, so problem B implies problem A, because you could look at the manifold to be the to say locally Euclidean means that there is a neighborhood of the identity which is homeomorphic to an open set in Rn. So it makes this topological group into a manifold. And so if you know the positive answer to problem B, you get a positive answer to problem A. So some remarks. So first of all, ES to B implies ES to A. So what's the status now then? A, ES to A is known. And this is the theorem of Montgomery. As you will see, it's based on the work of Gleason, a very important work of Gleason. And problem B is still open today. So people call it, nowadays people call this the Hilbert-Smith conjecture. It's known in some cases. It's known, for example, for Lipschitz. For Lipschitz homeos. It's known in dimension 2 and 3 also. So dimension 2, this is already Montgomery and Zicklin, and this is dimension 3, a recent work of John Pardons. It's also known that in order to solve problem B, so I won't be talking about problem B, but it's also known using the solution to problem A, which I'm going to devote this hour to, it's not difficult to see that problem B, a positive answer to problem B is equivalent to showing that ZP, the p-adic integers, cannot act faithfully. Cannot act faithfully like homeos on a manifold. So it's a genuine problem in topology. So somehow the group theory has been stripped down to Z. Okay. So what happened in 1952? So there are 3 papers. One by Gleason, 3 papers in the analysis of mass. Gleason shows that a locally compact NSS group is a lead group. So NSS means no small subgroup. So it means there exists some neighborhood of the identity without containing no subgroup, such that if H in G is a subgroup, such that H is entirely containing U, then H is the identity. Then, upon seeing the solution by Gleason to this problem, Montgomery and Zippin understand how to complete the proof and show that locally Euclidean group is NSS, and therefore it's a lead. And hence lead by this. Okay. So that's why it's very often attributed to Montgomery and Zippin, the solution to Hilbert's fifth problem. But it's also really based on, it builds on this work of Gleason. So I think the name of Gleason should not be forgotten from this solution. And then, just a year after that, 1953, Yamabe proves a structure theorem for locally compact groups. So he states this. So Yamabe's theorem. It shows that every locally compact group has an open subgroup which is approximated by lead groups. Now, what does this mean? It means that for every neighborhood U, neighborhood of the identity, there exists a normal subgroup of G prime containing U such that G prime mod A is lead and has finitely many components with finitely many connected components. So this is 1953, and then 1955, Montgomery and Zippin write a book, account on this, on the above. Right, so there's one more thing, there's one more thing I wanted to say about Hilbert zipping. So they show that locally Euclidean groups are NSS. They also show, so that's maybe statement 1, so to say. Also show statement 2, that if a group, if a locally compact group, acts faithfully. So in some sense, they solve problem B for transitive actions. So acts faithfully and transitively on a connected manifold, or more generally on a locally connected finite dimensional topological space, then G is a degree. So then G is a degree. Well, G, I mean, they show G is NSS. Right. So I will show you soon that number 2 here, as well as, so number 2 is a generalization of number 1, right? If you're locally Euclidean, you act on yourself transitively, faithfully. So 2 implies 1. I want to show you later that then Yamabe's theorem implies monomeric zipping theorem as well. Easy. Okay. So what should really go through to posterity is basically Yamabe's theorem. This is the stronger result, even though it's stated for arbitrary locally compact groups. So it's a structure theorem for locally compact groups. It's not exactly what Hilbert had in mind when he stated his fifth problem, because he was looking at action on manifolds. But this kind of result is basically a consequence of the structure theorem. So this Yamabe theorem is the more important. Okay. What was known before? So a quick review of what happened some years before. So in the 1930s. In the 1930s, Haar came up with a Haar measure. So this is Haar measure. That's an important thing. So this, at the same time, people on Cartan from Neumann theorem that closed subgroups of Lie groups are Lie. Groups. That's important ingredients as well. And another landmark result is the Peter-Weil theorem. So Peter-Weil is basically Yamabe's theorem in the case of compact groups. Says more. So it says that G is a compact group. then L2, so you can look, because you have a harmonic, you can look at L2 of G. L2 of G is isomorphic to a zeroth sum of representations. You can decompose L2 of G as a direct sum of irreducible representations. And they show that when G is compact, then the irreducible representations must have finite dimensions. So the dimension of sign is finite. And because it's finite, this means that you have a morphism into GLN for fixed n. So if you know that closed subgroups are Lie, so it's enough to conclude that Yamabe's theorem holds for compact groups. So namely that compact groups can be approximated by Lie groups. And for compact groups, you don't even have to go to an open subgroup. You have on the nose that every compact group has the property that every neighborhood of the identity contains a normal subgroup K, such that G mod K is a Lie group. Okay? And this G mod K will be the image of G under a few irreducible, fairly many irreducible representations. So so the proof is basically this. So the proof of Peter Weil is based on two facts. It's based on the existence of a Haar measure and on the spectral theory. So let me quickly remind you how Peter Weil is proved. So you take U a neighborhood of the identity, and you pick phi a Bell function supported on U. And you can assume that you can average it by, because of the Haar measure, you can average it. You can take a conjugate and average, and this way you can get a function which is conjugation invariant. And you can also take the average with phi inverse, and then you can assume this. So you have this nice bump function around the identity. And then you consider the convolution operator. Right? Then you set K phi the convolution operator, fiber, for the F function in L2. And you show that it's basically after the last column that K phi is a compact operator. And because of the choice of phi, it is also symmetric. It's also symmetric. So you can apply the spectral theorem for it, and the spectral theorem will tell you that the space L2 can be decomposed as a direct sum of say H lambda, where lambda is the eigenvalue, of phi, and phi is the Bell function, so it's positive, so K phi symmetric and negative. So the eigenvalues are positive, and you have this, and the fact that it's compact means, or implies, as part of the spectral theorem, that the eigenspaces are finite dimensional. Okay, so this gives you a representation. Right? And it's also a complete, you have a complete set of eigenfunctions. So this is the Hilbert direct sum. So this direct sum is dense in L2 V. So this means that you can that's like the Yamabe theorem is true. So if you take a small neighborhood around the density, then by taking so these lambda i's, they are bounded, they go to 0, and if you take sufficiently many but finitely many, then you can make sure that the kernel is very close to the identity. So that's how you get it. So the conclusion is that every conclusion is that every compact group, is the parts can be approximated by you. Okay, so in the same way, so approximated by groups means this. Okay, so every neighborhood of the identity contains a normal subgroup, modulo which I'm a B group.
So what's the relevance of the choice of U?
Yeah.
No. So the choice of phi. Phi is supported on U, and then.
Yeah. It's because you want eventually to be so this H number may not be irreducible. So, but you want it to be so that the kernel will be contained in U. The kernel of sufficiently many will be contained in U. Somehow you want that the representations that you see there, they separate point at resolution U. So what I said for Peter holds as well for abelian groups. If you have a locally compact abelian group, then it was known also, I think, in the 1930s that you have the notion of totally eigendual G hat is G is abelian. And you can write L2 of G as you can decompose it to a G again as there is a you can write it as a direct integral of one-dimensional representations. So again, you have a complete family of representations that allow you to prove Yamabe's theorem. So again, you get that G can be approximated. By groups. Okay. All right. So the statement that we are after, Yamabe's theorem, was known for compact groups and for abelian groups, and as we can see, a crucial tool was the Haar measure. So I guess people must have tried at that time to generalize this proof to non-compact, other locally compact groups. In particular, Gelfand and Raikoff showed that every locally compact group has a non-trivial unitary representation, and that unitary representations separate points. So you may think this is kind of a generalization of Peter, but this is not how the proof of the Gleason-Yamabe monogomerization theorem goes. It's not by representation theory. I guess part of the difficulty is that you can exhibit some unitary representation, but it's not going to be finite dimensional. So you don't know if the image is a unit at all. Okay. So however, the proof of Yamabe's theorem, so note, the proof of Yamabe uses photographs in several, twice actually, in key way. So there is no proof that does not use the spectral theorem. Okay. Let me sketch. So I said before that this statement of monogonalization follows from Yamabe. So let me sketch Yamabe implies monogonalization. So the setting is, again, we have G of R from X, basically, and transitive G. And X is locally connected. And finite dimensional. So note that it's actually very important that you are locally connected. If you're not locally connected, it's not true. So you're not a D group, because you can take, for example, the solenoids, say R cross Q2, not Z bracket 1 or 2. That's a nice compact group. It's connected, but it's not locally connected. And of course, it's not a legal. It's a connected compact group. Okay, so if you apply Yamabe, then you can assume, after passing to an open subgroup, you can assume that G is approximated by these groups. Okay, because then you just restrict to the orbit, some orbit of G prime. This orbit will be open and going to stay locally connected and dimensional. So, okay, so you have that G is approximated by D groups. I can write this like that. It's like a projected limits of D groups. So let me call it G sub n. G sub n is G mod Kn, and Kn is normal in G, and Kn tends to the energy. So then you can look at Xn, which is X mod Kn. and so x, the action is transitive, so x is some g mod h, some x. Okay, so xn will be gn mod hn, where hn is like hgn or tn. Okay, and the gn's are the groups.
HKN.
Thank you. Okay, so yeah, so the x is so x is locally connected. So these are locally connected as well, and so xn. So Gn is the group. So so Gn mod Hn is the manifold. So this means that your x is approximated by manifolds. And you know that x is finite dimensional. So this implies that there is a bound on the dimension of the manifold. This means that so x is finite dimensional implies that this human dimension xn is finite. So this means that after a certain point, the dimensions are the same. Which means that xn is a cover of xn naught. And the group of deck transformations is basically k and naught over kn. And so this k and naught, because that's compact, so it must be finite. Okay, so you have this tower of covers, finite covers of x and naught. And you know that at the end, the space you get is locally connected. The only way this can happen is if there is an upper bound on the size of this quotient. The group of deck transformations, when if n tends to infinity, kn goes to the n-entity, so kn naught is a profinite group. But you see that the fiber, in order for the fiber above a point in x n naught, in order for the fiber to be, in order for the pre-image of a small open set in x n naught to be locally connected in x, you need this limit group k n0, this profinite group. You need it to be finite. If it's not finite, it's profinite, then it will violate local connectedness of the protected limit. So if x is locally connected, implies this implies k naught is profinite. but this implies that K moves now. And so that's it. So this means that G is a Lie group. Okay, so this is basically the way this theorem can be deduced from the Montgomery-Zipin theorem can be deduced from Yamabe. Sometimes the Montgomery-Zipin theorem is stated in a slightly different way. So in fact, in geometry group theory, we are used to this theorem because Gromov uses the Montgomery-Zipin theorem. And if you look at Gromov's paper, he states a slightly different theorem that he calls Montgomery-Zipin. And he says it can be easily derived from a certain statement in page 263 of Montgomery-Zipin book. So let me tell you what this is about. So this is a note, sitting aside. So Gromov, in his putting in the growth paper, uses the following statements. If X is connected plus locally connected a metric space, so this time it's a metric space of finite dimension, with the property that the isometry group is transitive, then the isometry group is a Lie group with a finite number of connected components. So this is what is often quoted as the Montgomery-Zipin theorem, but it's not explicitly stated in the book. So let me show you why this also follows from Yamabe. So note that in Yamabe, in the version I stated before, the Montgomery-Zipin, I'm not claiming that the group has finite. I claim only it's a Lie group. I'm not saying there are finitely many connected components. Indeed, there's no reason that there would be finitely many connected components. You could act a Lie group with infinitely many connected components can very well act transitively and faithfully on connected them. So, but here it matters that it's an isometry group.
You are assuming that X is locally compact.
Yes, and I forgot one thing. Thank you. And X is locally compact. So, so because X is locally compact, G must also be locally compact. So then you can apply Yamabe, and you get G prime open in G, which is approximated by Lie groups. And then you say, okay, so G acts on X transitively. So you can write X as some G mod H, where H is a stabilizer of a point. Then you argue that because it preserves the metric, H must be compact. And so this means that G prime times H is closed and open in S. So since X is connected, so it's closed because H is compact. It's open because G prime is open. And since X is connected, X is equal to G prime times X naught of X. And so this implies that G is equal to G prime H. And so so now you can apply the above proof by the above proof of this regular hidden statement. You get that G prime is a Lie. Okay, G prime is a Lie group, so because G prime is open in G is a Lie group, but H is compact, so this implies that there can be only finitely many connected components. And so this is somehow the missing bit in Nicolas' paper, which sometimes just people say it's a black box. It's okay, but that's how it can be derived from Yamabe style. What?
Why H is?
H is compact because we assumed that H is a stabilizer of a point and it fixes the metric. Because it's an assumption.
And the proof that the isometric group of X is locally compact proves more. It proves that the G action on X is proper.
What? So in particular.
Yeah.
Yeah, that's right. Okay. So, I mean, so part of my aim here in presenting you this is to try to demystify a little bit this Morgenberg-Zippin statement and basically say that, okay, what the important theorem is Yamabe. Or sometimes we call it the Gleason-Yamabe theorem because Yamabe just builds on Gleason's ideas. So, okay, so now I'm gonna get in there. So, some remarks. So, some remarks. First, I want to say that Yamabe's theorem is a local statement. So this means it's really, everything happens really near the identity. It doesn't take into account the global structure of G. And indeed, it only says something about some open subgroup of G. And it turns out that the proof can be adapted to not locally compact groups, but locally compact local groups. So you actually don't need to have a group. All you need to have is a kind of a germ of a group. So you need to have a space, locally compact space with identity, where the multiplication is defined only for pairs that are sufficiently close to the identity in some neighborhood. You don't care if it's defined away from the identity. So this version is, was proved by Jacobi in the 1950s, which is Yamabe's theorem for local groups. And it's sometimes useful for people doing transformation groups. This had quite a number of applications. But it was realized in the 70s that this proof was flawed. It's a serious mistake. Part of the reason was that I think not so many people understood the original argument of Gleason-Yamabe and Morimer-Zippi. So they had it was easy to make a mistake. And then very recently, 2008 or 10, the mistake was filled, or the theorem was reproved by Isaac Goldring. In the announced paper. And so this paper is a bit like the culmination of many years, decades of simplifying the proof, understanding much better what goes into the proof, and also Goldring is a model theorist, so people realized over the years that the proof can be formulated more easily in the language of non-standard analysis. It's somehow, when you read Gleason and Yamabe, they're always taking subsequences, doing a diagonal argument, taking another subsequence, another diagonal argument. It's using Arcelor-Ascoli all the time. And so you do this, every line you use Arcelor-Ascoli, you take a subsequence. So it's a bit difficult to read. But model theorists, starting with Hirschfeld in the 70s, have taken the task of rewriting the proof of that theorem in using the language of non-standard analysis, and more recently model theory. And so it was quite successful. Hirschfeld already managed to give an account, which is quite short, although he didn't give a full account, but still has some very interesting simplification in this work. And more recently, Van den Dries and Goldring had a seminar on Hilbert's fifth problem, and they wrote some notes which are now published in Enseignement Mathématique, which gives a non-standard treatment of the proof, and basically the proof takes 10-15 pages. It's much easier to read. Okay. I should say that before that you had a book by Kaplansky, which introduced this Chicago Blue Book, which introduced some further simplification. This was in the 60s, but now you can find 2000 you can find a modern treatment in Charles' book. It's a modern treatment, but so there are. If you don't like non-standard analysis, then you should look in Tao's book. This is a standard treatment. If you have a liking for it, I advise you to take a look at Van den Dries and Goldring. Quite nice. So, now I can tell you a little bit about proof for the Yamabe theorem. So, the proof is based on two lemmas, which are now called the Gleason-Yamabe lemmas. And their formulation, I mean, they are not formulated like that in the open papers. Their formulation is essentially due to Hirschfeld. Gleason-Yamabe event variables. Okay, so the setting is this. So G is locally compact. Is a locally compact group. And U is in a compact neighborhood of the density. And then I'm going to introduce this notation. N sub U of G is the supremum largest integer such that 1, G, G squared, and N belongs to U. So you have the density here, you have some points G, and then you look at G squared. If you look at the first time, you get out of U. Okay. Take tabs. So the proof of the Gleason-Yamabe theorem is really based on trying to understand that function. Okay, so that's try to say what. So you start with the so as I said at the beginning, there are two parts of the proof, right? So if you want to prove Yamabe's theorem, first you want to reduce to the NSS case, and then you want to prove that NSS is Lie is Gleason's theorem. Reduction from arbitrary locally compact to NSS, so is Yamabe. So Gleason is NSS implies Lie, and Yamabe is locally compact implies approximated by NSS. So there are two parts. There are two parts in proof. And the two parts use the Gleason-Yamabe lemma, and the two parts use a study of this function. So, in the same way, if I have Q any subset of U, I'm going to let N U of Q to be the same thing. Supremum N at 1 Q squared Q to the N is entirely contained in U. So I look at the first time, I have a small subset Q here, and then I look at Q squared and so on, and look at the first time Q to the N plus 1 eventually pops out of U. Okay? And finally, I want also to look at the inverse of this. I define the inverse of this integer, and I call it the escape rule. T with respect to U. Okay, so that's my notation.
What's the little hat on the equal sign?
It's a definition. So there are two lemmas. So here's the first one. Number one. First one assumes NSS, so assume G is NSS. And yes, U and V is small enough compact neighborhood of 1. So this means there exists a compact neighborhood such that for every human being containing it. Then there exists a constant C depending on your human being. Such that mu of Q. So these two quantities are comparable. So it takes roughly the same amount of time for powers of Q to get out of U or to get out of V. Then there are these properties of the escape norm. So this is the group commutator. So this last one says that the group commutator of G and H, its escape norm is bounded by the product of the escape norms. The second one says that the escape norm of the product is bounded by constant times the escape norm of both of them. So for example, let's consider. So let's see, get a feeling for what this means.
In this property one, is the constant independent of G and H?
Yeah, for every G and H in U.
Oh, okay.
C is the same constant as in 0.
Right. Or another one that depends on you. So let's see what number 2 means, for example. What it implies. It means that if all powers of G and all powers of H, so if powers of G take a certain time to escape, and say powers of H also take the same amount of time to escape, then the powers of GH will take at least the same amount of time to escape. So G takes a certain amount of time to escape, H also, then GH will remain in U for a long time, at least roughly the same amount of time. So first a remark, that if you know if G is equal to Z, then this is very easy because we have an exponential map. Okay, so then we know that if you take usually takes of some small bulk, and then you see that the escape norm of, let's say, x of x is up to the multiplicative constant, the same thing as the norm of x. Because of the exponential map. The time it takes to get out of a fixed neighborhood is basically this size, the log. Okay. So this is all obvious if you're but of course we're trying to build the exponential maps. And same for the commutator, but the bracket is a bilinear form, so it's it's fairly easy to see the number 0 here. Because if this was not true, so you can, to see number 0, you can assume that U is contained in V. And if this was not true, then this means that you could find sets Q very small, compact sets very small, close to the identity, with the property that they, at some point, they escape U. So suppose U is contained in V. So at some point they escape U, but then they will escape, it will take them a much bigger amount of time to escape V. So suppose n U of Q and V of Q are not comparable. So then it means that you have some subsets Q very close to the identity, which take a certain amount of time to escape U, but to escape V, they take maybe 100, 1,000, 10,000 times longer. Then you see that you can take a limit of this diagonal argument, subsequence, take a limit using local compactness. What you get at the end is a compact subgroup contained in V. Compact subgroups of a group are subgroups. A compact subsumgroup of the project group is group. So it gives you a small subgroup. It gives you a subgroup containing V. Okay. So 0 here is just is a simple consequence of NSS. One just follows from 0. 0 implies 1. If you take U to be, say, U which is about 3. Because G and H are in U, so. Um, 2 and 3 are the really difficult parts. This is the VPC. So in particular 2, and 3 will be proven similarly. 2 is the difficult part. So in fact, if you read the sales Bourbaki report, that's just a year before Gleason shows that NSS implies U. And he explains Peter Varley, explains everything, and he says that basically he says that if we knew that, we would be done. If we knew that whenever you take a small q, so yeah, if you that if maybe I'm saying this ahead of what I want to say. Let me just state the second lemma, and then I will explain what sales comment was about. So the second lemma is about the reduction to NSS. So you don't assume, so G is just local compact. Okay? Don't assume NSS. And the lemma says that V be a compact neighborhood form. And then there exists some constant V, CV, such that for every K, every number K, there exists U in V, neighborhood of 1, such that for every subset Q in V, either n V to the 4 of Q is bigger than K times NV of Q. So either you see so K, think of it as very large. Either they are not comparable in this quantitative way, or there exists G and Q such that NU of Q is less than K times CD NG of Q. That's lemma 2. So what does it mean? So let's say, suppose you are NSS. Suppose you are NSS. Then by what we said, n sub v to the 4 and n sub v are comparable. If k is large enough, then this never happens. So then you're always in this case. Case, the second case. So if you are NSS, this means that whenever you take a small neighborhood, or a small subset Q, not neighborhood, any subset, so containing the identity, and you take its powers, e to the n, and you look at the first time it pops out of V, then this first time is comparable up to constant to the first time an individual power of an element G in Q escapes Q. So these two times, which a priori have nothing to do with each other, are comparable. So it means that if there is a word, in other words, if there is a word with letters inside Q, that you may use different letters in words, not just one power. If there is a word that is fixed at a certain time, then there is an individual guy in Q whose powers escape. Also escape at the don't take much longer to escape. So this is the statement that says, say, if we knew that, we would be done in 1951. So this is what Gleason did, showing this in the NSS situation. And Yamabe, we find Gleason's construction to handle the non-NSS case, showing this dichotomy. So this dichotomy uses Peter by proof, not the proof of the lemma, but the proof that so lemma 2 implies that you are approximated by NSS. And what goes into here is basically Peter by. Because if you're not NSS, then you're going to build. So this will tell you this lemma here. So I'm not going to explain everything, but this lemma here has a consequence corollary, which is easy of lemma. Is that there's a subgroup trapping lemma. Subgroup trapping. And so it says that for every V, there exists U, such that the subgroup generated by all subgroups of V contained in U, this subgroup is contained in U. That's the key point. And so, yeah, so given a small neighborhood, you can find a smaller one, such that if you look at all subgroups, in particular, if you have just powers or cyclic subgroups that are contained near their density, the subgroup they generate is relatively compact. And you see how this implies number 2 here. Because you can take Q to be just the pair GH. And it says that if there is a word in G and H that escapes at a given time, then either G or H will escape at the same time. It will not take much longer to escape. So the escape of GH to some power is a word in G and H. So this means this.
So the logical order in the proof is that lemma 2 combined with Peter line
So yeah.
implies corollary, implies lemma 1.
Yeah, so lemma 2 implies the reduction to NSS. And this corollary to the lemma of the circle trapping property. It also implies number 2 of lemma 1. Number 3 of lemma 1 is proven in a similar way as the proof of lemma 2, which I'm going to say one thing about in the next. You use Peter Vine because if you know Peter Vine, then you know that compile groups are approximated by E groups, so you know they are locally approximated by NSS groups in particular. So you see that now that you have this subgroup trapping property, so this subgroup, the proof of this corollary uses Peter Vine. So the idea is because it's compact, so you know it's compact, so you know Peter Vine. So you could. Another thing I should say, maybe before I erase the lemmas, let me tell you about the structure of the proof of. So this is Yamabe's theorem. Okay. Now, what about Gleason? What about NSS implies Lee? Gleason. So NSS implies Lee uses lemma 1. And let me tell you in what way. So first there is a result that Gleason had some years before, which is that in NSS groups, these NSS, then the square root is well defined near the identity. Square root of normal. Is so given every x near the ns, either you should limit y squared equals x. That's not so difficult to show, just using NSS. And so you can take iterated square roots and take powers. So this implies that every element near the identity lies on a one-parameter subgroup. Every x near 1 lies on a one-parameter. And so what are we trying to do? We're trying to show it's a group, so we're trying to build a D algebra and an exponential map. So we can easily talk about one-parameter subgroups. How do we build a Lie algebra? Well, we are going to say, let's take the set of one-parameter subgroups. Set.
What's your definition of one parameter subgroup here?
Continuous homomorphism from R plus 2G. You take the set of all of those, and you want to put a vector space structure on them. Okay, so you don't know how to define addition first. How do you define addition? So you are guided by the fact that in Lie groups you have this formula. If you take x of t and it's a y of s, two one-parameter subgroups, then so two elements of the algebra, then you can define, you know that x plus y is the limit as n tends to infinity of x of t over n times y of t over n to the power n. So this is the formula this is the formula in the theory of Lie groups or matrices, right? If you have an exponential map, then this is certainly true. So if you have an exponential map, like here x of t is e to the x times t, and it takes some element in the Lie algebra. Okay? So that's how, if x is an element in the Lie algebra of the Lie group, then this holds. Right? If I'm in, but if I'm not in Lie group, I can use this formula to define addition. I start with two one-parameter subgroups, x of t and y of s. I can do the product to the power n, and if I can take the limit, then I want to say this limit is x plus y of t. Okay? So the question is, why does the limit exist? So why does it exist? Can I take it? One problem is that it could be that it goes to infinity. There's no limit; it goes to infinity when I take this power. So it could be that this product the powers of this product escape much faster than the individual. And this is exactly what this lemma tells you. This does not happen. This part 2 here tells you that this power of this product does not escape, remains bounded. Okay? And so, remains bounded. It doesn't say there is a limit. But in order to show its limit, you need to use the third one. You need to show that the third guide allows you to prove that this is a quotient sequence. So by local compactness, there will be a limit. That's how you define the sum. And then you have to show that you also have a scalar multiplication by scalar. That's easy, so it becomes a vector space. And then you need to prove that this vector space has finite dimension. But given that we know that every element is in some one-parameter group, we already know that, so this will get used to prove that this vector space of one-parameter subgroups is locally compact. Because near the identity, it looks like the neighborhood of the identity in G. So from there, you show that this is locally compact. And locally compact topological vector space must have finite dimension right there. So it's finite dimension. Okay? And then it's finite dimensional, and then you have, of course, conjugation action. You can conjugate, and because of this, you know that the action that it makes sense to conjugate gives you a bounded operator. So this way you define add to GL of your Lie algebra. Lie algebra is defined as the vector space of one-parameter subgroups. And it's finite dimensional, so this ad is a very nice representation. And you know that the kernel uses the center. And you know that for a billion locally compact groups, everything was done before, they are approximated by Lie groups. So here we have a Lie group, before we have something, we have a kernel, which is also approximated by Lie groups. And then, so it's an extension of two things, and then that's enough to show that G itself is approximated by. It is a Lie group in this case, because we assume it exists. So that's how the proof goes. Now, I didn't tell you yet how to prove the lemmas. So, I'll be brief on this. Anyways. So the idea is, again, it's like in Peter Lie. You take a bump function around the edges. So it's the idea. Lemma one. So you pick phi to be a bump function. Mu, so support of phi is something like mu. Phi has value 0, 1, and you assume that phi of 1 is 1. Okay? And what you would like to say, would like to say that this escape norm is comparable to the an infinity norm of the difference of the formal derivative of phi. So what is this? By definition, this is just phi of g inverse x minus phi of x. Okay, so that's by definition what I would denote by partial d phi. It's phi of g inverse x minus phi of x. Why do I say that you would like to write that? Well, because because this is what happens in a D group, first of all, and because what you know is a triangle inequality. That's easy. You know that delta pH phi is less than delta p phi plus delta h phi by formally. And you also know that if delta of g, the norm of partial g phi, is strictly less than 1, it implies that g belongs to the support of phi. So it belongs to you. Why? Because if G is not in the support, if G is not in mu, then phi of G is equal to 0. So delta G phi of G is equal to phi of 1, which is 1. So if the infinity norm is strictly less than 1, certainly G belongs So, and so these two facts combined together implies easily that the escape norm is at most, let's say, twice the L infinity norm of the derivative, the partial derivative. Because if this is, let's say, smaller than 1 over n, then all powers will be less than 1. If you know that this is, let's say, less than 1 over n, which implies that 1, g, and so on, g to the n belong to you. Because they will, by triangle inequality, be always less than 1. So they all belong to you. Okay? So it means that the escape norm is at most 1 over n. Yeah, of this. And and so you have the triangle inequality. So you see, if you could have the opposite inequality, you would immediately get this number 2 of the lemma, which I erased. If I knew that, this triangle inequality will work for the escape norm, and I will be happy. So it's difficult to show the other way around, and that's the brief of the lemma. And so the idea is to look at this Taylor expansion. So the thing is that if you knew that everything was, let's say, C2, then it would be easy to show that delta g to the n phi would almost be equal to delta g to phi, because you have the following Taylor expansion. Delta of g to the n phi, that's a formal delta Taylor expansion, which is always true. This formally, you have that, this equation, these two formally. So, so if you could somehow show that this is an error term compared to this, then you would have that, and this will tell you that you have the converse inequality. These two things are actually comparable. If you know that your function is C2 on the D group, then as long as g to the I is close to the identity, then this will be negligible because of this derivative. This will be negligible compared to delta g of phi. So this whole term will be less than n times delta g of phi. It doesn't work if you have no regularity. And the idea of Gleason is to cope with the absence of regularity by using the harmonizer, by using convolution. So the idea of Gleason is to pick phi as psi 1 involved with psi 2 for certain suitable psi 1 and psi 2, so that when you take a double derivative, you'll see that this is the integral of psi 1 of y, psi 2 of y inverse x, d1 from the Harmonizer. And when you take this formal derivative, you see that it's delta g psi 1 of delta h conjugate with g on 2 of 1 inverse x dy. So you have this formula which you can check, it's completely formal. But as a result, if you have some control on the first derivatives, you get a control on the second derivative, thanks to this convolution trick. convolution regularized the function phi. And so this is what goes into, this is the main idea, to establish the lemma. Because then you can see that with this particular phi, this would be negligible compared to the main term. And then the term. Okay, so thank you. So how measure it?
So this trick, how is it adapted in the local group situation?
Yeah. Yeah, it works also. You would just take Hall measure, the local Hall measure. Everything is local, you know, everything is supported with small neighborhood density. And in fact, as a consequence of all that, you get that a locally compact group has the same germ as a genuine locally compact group. So there's no difference. There's no new locally compact group. Local. Which is, I think, not true for infinite dimensional unions. But it's another story.
Then you could do next week.
Next week, I will attempt to give you some ideas of, of the proof of the structure theorem for proximal groups. Tell you how to adapt these lemmas to our setting, and maybe give you some application.